In a galaxy far beyond the reach of any telescope, billions of light years from Earth, a star more than 100 times heavier than our Sun reaches the inevitable end of its life. For one fleeting instant, it unleashes more energy than 1 trillion suns combined, detonating with a force so staggering it shakes the very fabric of spacetime. Ripples of that final heartbeat travel outward for billions of years, carrying the memory of a death so violent it can remake galaxies. Tonight, we venture into realms where ordinary understanding collapses, where nature plays by rules so extreme they twist reality itself. Here, explosions burn brighter than entire galaxies, black holes swallow even light, and hidden forces stitch the universe together at scales smaller than imagination. This is not merely the story of stars, it is the story of creation, destruction, and the relentless laws that govern every atom of our being. Inside you, within the atoms that form your body, an invisible war has raged since the birth of the cosmos. At the core of each atom, protons, all positively charged, should repel one another with incredible violence, like trying to crush two of the strongest magnets in existence together. Logic says the nucleus should tear itself apart, yet it holds, firm, bound together by the strongest force in the universe, the strong nuclear force. This force is staggering in its intensity. It is 100 times stronger than electromagnetism and 100 trillion times stronger than gravity. If gravity were a whisper, the strong force would be the thunder of a mountain collapsing. Its messengers, particles called gluons, act as invisible chains binding quarks into protons and neutrons. Try to pull them apart, and the force resists. Harder, stretching like a cosmic rubber band that only grows stronger. This peculiar behavior, confinement, means no quark can ever be free. When you attempt to sever one, the universe answers by creating more. New quarks, new gluons, new links in the endless chain. These battles play out on scales so tiny that even a femtometer, a quadrillionth of a meter, seems enormous by comparison. At such scales, the familiar rules of physics vanish. Space seethes, time flickers, and the laws of quantum mechanics take over. The strong force decides which nuclei can exist, fuels the furnaces of stars, and determines whether the universe blazes with light or lies barren in eternal darkness. Without it, no protons, no atoms, no stars, and no life would ever have formed. And yet, despite its unimaginable strength, its reach is limited, confined to the tiny prisons of atomic nuclei. Beyond those walls, other titans of the cosmos take control. Step farther into the universe, and distance rewrites the rules. There, cosmic forces collide in spectacles so violent they defy comprehension. Imagine a beam of pure energy tearing across. Space at nearly the speed of light, focused with such precision that it stays narrow across millions of light years. For mere seconds, it pours out more power than our sun will in its entire 10 billion-year lifetime. This is a gamma-ray burst, the most violent explosion in existence. These apocalyptic events occur when the most massive stars collapse. Their cores implode under gravity's merciless pull, creating newborn black holes surrounded by swirling disks of superheated matter. Twisted magnetic fields act like cannons, hurling twin jets of energy into the cosmos at nearly light speed. These cosmic bullets punch through the dying star's shell, racing outward with terrifying focus. To imagine their precision, picture a laser holding its aim steady from Earth to the nearest star, and then multiply it 1,000,000-fold. The energy released in a single burst can outshine 1 trillion suns. The brightest ever detected, the BOT, brightest, of all time, flashed across the universe in 2022. It was so intense it overloaded detectors across the solar system and disturbed Earth's upper atmosphere, even though it erupted 2 billion light-years away. That light began its journey when life on Earth was still single-celled, crossing an unimaginable gulf of time to reach us. Some gamma-ray bursts carry messages from the dawn of the universe, when the first stars blazed less than 1 billion years after the Big Bang. Their deaths seeded the cosmos with the heavy elements that would one day form planets and life. But even these titanic explosions are eclipsed by the monsters lurking in galactic hearts. At the center of our own Milky Way waits Sagittarius A, a black hole 4 million times more massive than the Sun. But across the cosmos exist behemoths, far greater, black holes weighing 40 billion suns, compressed into regions smaller than our solar system. Their gravity bends light, time, and space itself into a whirlpool of darkness. Some of the earliest quasars, shining from when the universe was still an infant, are powered by black holes that amassed billions of solar masses in cosmic heartbeats. Their very existence challenges our understanding of how anything could grow so impossibly fast. The process by which these monsters feed is as violent as it is spectacular. Gas spirals inward, heated by friction to millions of degrees, creating disks brighter than 100 billion stars combined. Near the edge of the abyss, matter races at nearly the speed of light, experiencing time so distorted that seconds stretch into hours for distant observers. When these quasars blaze, they become cosmic lighthouses, visible across the entire observable universe. And still, some black holes do not merely consume. They reshape galaxies. Their jets of plasma, flung outward at near light speed, stretch hundreds of thousands of light years, heating interstellar gas to millions of degrees and quenching the birth of new stars. For millions of years, they pour energy into the cosmos, sculpting galactic evolution itself. Recent discoveries show some black holes so oversized for their galaxies they defy every known law of cosmic growth, hinting at secrets science has yet to grasp. Yet, even these giants yield to a greater mystery. Across the universe, an unseen hand pushes galaxies apart, stretching space-time itself. This is dark energy, the invisible force accelerating the universe's expansion. It accounts for nearly 70% of all cosmic reality, yet we have no idea what it truly is. First glimpsed in the 1990s through distant supernovae, dark energy stunned scientists. Instead of slowing, the expansion of the universe was speeding. Up galaxies carried apart as if on a swelling ocean. Imagine a balloon inflating endlessly, every point drifting farther from every other point. This force does not weaken. As the universe grows, more dark energy appears, accelerating the expansion further, as though space itself generates its own fuel. Its behavior defies one of the most fundamental principles of physics, the conservation of energy. It may be a property of space-time itself, a cosmological constant Einstein once abandoned as his greatest blunder, or perhaps a dynamic field evolving with time. Some whisper it may demand an entirely new understanding of gravity. For now, it remains the universe's deepest enigma, the silent hand guiding the cosmos toward a fate we cannot yet predict. The consequences of dark energy are both awe-inspiring and terrifying. In the distant future, it may tear apart everything the universe has built. Galaxy clusters will drift into isolation, bound no longer by gravity. Individual galaxies may unravel, And ultimately, in a hypothetical event called the Big Rip, even atoms themselves could be stretched apart. Stars will die, planets will drift, and matter itself may be pulled asunder, leaving a void where the universe once thrived. Among the cosmos' more immediate horrors lie neutron stars, remnants of massive stars compressed to extremes that defy comprehension. Imagine taking a mountain and crushing it to the size of a sugar cube, and even then it would be far less dense than a neutron star. These stellar corpses pack the mass of the sun into a sphere just 12 miles wide, creating gravitational fields so intense they warp light and bend spacetime into impossible shapes. Gravity is only the beginning. Neutron stars often possess magnetic fields 1 trillion times stronger than Earth's protective magnetosphere, capable of trapping charged particles and accelerating them near the speed of light. These beams of radiation sweep across space like cosmic searchlights powered by the fundamental forces of the universe itself. The magnetic field is so intense it could erase every credit card on Earth from 600 meters away, and at 1,000 kilometers, it could even strip iron from your blood. These magnetic fields channel streams of particles into narrow beams. When the star spins, it becomes a pulsar, firing beams of radio waves and X-rays with astonishing precision, some rotating 600 times per second, faster than a kitchen blender, yet keeping perfect time rivaling atomic clocks. Each pulse marks another rotation of a stellar corpse spinning in the darkness. On their surface, physics as we know it breaks down entirely. Atoms stretch into needle-like shapes aligned with the magnetic field, and ordinary matter is compressed into layers mere millimeters thick. Drop a marshmallow from waist height, and it would strike the surface with the explosive force of a hydrogen bomb, releasing more energy than all explosives used in human history. Some neutron stars, called magnetars, push these extremes further, 1,000 times stronger than typical neutron stars, approaching the maximum magnetic field strength allowed by physics. When these stellar remnants experience magnetic quakes, their crusts crack and shift with unimaginable violence. In a fraction of a second, just 1/10 of a heartbeat, they release more energy than our sun produces in 100,000 years. These magnetic cataclysms ignite giant flares that can be detected across the galaxy, making their presence known even from tens of thousands of light years away. The most powerful magnetar flare ever recorded briefly affected Earth's upper atmosphere, despite occurring 50,000 light years away, a stark reminder of the reach and potency of these cosmic titans. The magnetic fields surrounding magnetars are so extreme that they distort the very vacuum of space. This once invisible void becomes birefringent, acting like a crystal that polarizes light passing through it. Observations of this effect provide astronomers with direct evidence of field strengths far beyond anything achievable in terrestrial laboratories, a glimpse into the raw, untamable energy at the universe's extremes. But magnetars are only the beginning. Stretching across the observable universe could be cosmic superstrings, invisible threads that could slice through planets as easily as wire through cheese. If they exist, these one-dimensional objects are thinner than a proton, yet potentially longer than entire galaxy clusters. Born during the first fractions of a second after the Big Bang, they are remnants of phase transitions in the universe's fundamental fabric, scars from the birth of space-time itself. Imagine the universe as a frozen pond, cooling from a state of perfect symmetry. Cosmic strings are the cracks that form as different regions solidify in slightly different ways, marking boundaries etched into reality. A string just 1 meter long could weigh as much as Earth, yet remain so thin it is effectively one-dimensional, existing at the boundary between existence and nothingness. matter and energy, reality, and pure mathematics. The energy within a cosmic string is beyond comprehension. A string stretching from Earth to the Moon would contain enough mass energy to power human civilization for trillions of years. And yet, it occupies almost no volume, an ultimate expression of concentrated energy. If these strings move, they send ripples through space-time itself, generating gravitational waves detectable by our most sensitive instruments. Unlike waves from black hole mergers or neutron-star collisions, cosmic string signatures would be unique, a direct imprint of the universe's earliest moments. When cosmic strings intersect, they can form loops that oscillate like cosmic guitar. Strings vibrating not with sound, but by sending gravitational waves racing outward at the speed of light. These loops gradually lose energy, shrinking over millions of years until they vanish in a final pulse of space-time distortion. Some theorists speculate that cosmic strings could act as cosmic highways, enabling faster-than-light travel through folded space. Others suggest they are glimpses into extra dimensions, one-dimensional shadows of higher-dimensional objects. For now, these theoretical titans remain hidden, waiting to be discovered or disproven by future observations. Meanwhile, billions of light years away, supermassive black holes are performing cosmic feats of unimaginable power. 4 billion. Light years from Earth, one such black hole launches a jet of superheated plasma that stretches across an entire galaxy, moving at 99.9% the speed of light. This stream of particles carries enough energy to power a trillion stars while maintaining a focus and coherence that defies human comprehension. Quasar jets are born from chaos. Matter spiraling into the supermassive black hole forms an accretion, disk spinning at near light speed. Magnetic fields twisted by this rotation act as natural particle accelerators, channeling material into narrow, collimated beams that shoot outward from the black hole's poles. Matter that should be dragged into oblivion is instead ejected at relativistic speeds through a magnetic catapult, guided with perfect precision as if by a cosmic ruler. These jets remain narrow and perfectly straight across hundreds of thousands of light years, observable as thin lines of light even from billions of light years away. Particles within these jets carry energies millions of times greater than the most powerful particle accelerators on Earth. Protons accelerate to speed so close to light that their relativistic mass increases by thousands of times, turning ordinary matter into cosmic bullets of near-limitless power. When a jet points directly at Earth, we perceive it as a blazar, its light sweeping past us like a lighthouse beam. The brightness of these blazars can fluctuate by hundreds of times in mere days or hours, as turbulence in the jet produces knots of emission moving toward us at apparent speeds faster than light. This superluminal motion is an optical illusion caused by geometry, highlighting just how close these jets come to the universal speed limit. The most powerful quasar jets can influence their entire galactic neighborhoods. They heat interstellar gas, create immense cavities, and suppress star formation across millions of light years, effectively sterilizing entire regions of space. Observations reveal jets extending far beyond their host galaxies into the intergalactic medium, propagating energy for millions of years, an eternal testament to the cosmic power unleashed by supermassive black holes. These ancient jets of energy carry the signatures of black hole activity from cosmic epochs when the universe was younger, denser, and far more violent than today. Across 30 million light-years, in a distant binary star system, a white dwarf is quietly siphoning hydrogen from its companion, a cosmic vampire feeding on stellar blood. For millions of years, the gas flows steadily, layer upon layer, accumulating, like snow on a mountainside, building toward a catastrophic threshold. White dwarfs are the dense remnants of stars like our Sun. The leftover cores once nuclear fusion ceases and outer layers are expelled. They pack the mass of our Sun into a sphere the size of Earth, creating matter so dense that a single teaspoon would weigh as much as a car. Their surfaces blaze at tens of thousands of degrees, hot enough to vaporize any known material. The stolen hydrogen compresses into a thin shell under the dwarf's extreme gravity, heating slowly until nuclear fusion ignites in a smoldering inferno across its surface. When the white dwarf reaches 1.4 solar masses, it crosses the Chandrasekhar limit, the maximum mass electron degeneracy pressure can sustain. Beyond this point, gravity triumphs. The accumulated material detonates in a runaway thermonuclear explosion, ripping the star apart in mere seconds. The detonation races through the white dwarf like flames through cosmic dynamite, fusing carbon and oxygen into iron and nickel, consuming the star entirely. This is a type Ia supernova, one of the universe's most precisely violent events. Each explosion releases nearly the same energy, making these cosmic lighthouses perfect standard candles for measuring distances across billions of light years. The brilliance of a single white dwarf's death rivals entire galaxies. For weeks, its light outshines hundreds of billions of stars. Radioactive decay in the ejected elements sustains the glow, scattering calcium, iron, and nickel across space. The very elements that now form our bones, our blood, and even the coins we use. We are, quite literally, children of stellar ashes, remnants of these cosmic crematoriums. Shock waves from a type Ia supernova blaze outward at thousands of miles per second, heating surrounding gas to millions of degrees, triggering waves of new star formation while enriching the environment with heavy elements essential for planetary systems. Elsewhere, an even more violent ballet unfolds. Two neutron stars. The crushed cores of massive stars spiral toward each other in a gravitational death dance that has lasted millions of years. Each star packs more mass than the Sun into a sphere just 12 miles across. Their surface is so dense that a teaspoon weighs 6 billion tons. They are the densest matter possible without collapsing into black holes. As they orbit, the stars distort each other's shapes, stretching and squeezing under tidal forces, generating heat that turns their surfaces into glowing furnaces of millions of degrees. Energy bleeds away through gravitational waves, ripples in space-time racing outward at light speed, imperceptibly stretching and compressing reality. Advanced detectors on Earth can sense these waves, measuring distortions smaller than 100,000th, the width of a proton. In the final seconds, the neutron stars whirl hundreds of times per second, a frenzied spin faster than helicopter blades. The gravitational waves surge, carrying away energy equivalent to 3 suns in just the last few seconds. When they collide, the universe shudders. A brief gamma-ray flash erupts, followed by a kilonova, a longer-lived explosion radiating with the brilliance of hundreds of millions of suns. This cosmic collision forges the heaviest elements in the universe. Atomic nuclei are bombarded with neutrons so rapidly they can barely stabilize, creating unstable isotopes that decay into gold, platinum, uranium, and other precious metals. A single neutron star merger can eject several Earth masses of gold, dispersing it across space to seed future planets and asteroids. Debris travels at speeds approaching 1/3 the speed of light, the fastest material in the universe, forming both the initial gamma-ray burst and slower radioactive shells that glow for weeks, and yet these violent events are only the latest chapters in a story that began 13.8 billion years ago. At the dawn of time, all matter and energy in the observable universe were compressed into a point smaller than a proton. Every galaxy, star, and particle we know existed in a singularity of infinite density. This was the Big Bang, the ultimate release of cosmic power, the moment when existence itself ignited. At this primordial instant, the laws of physics as we understand them broke down completely, a realm where time and space had no meaning, and every possibility lay poised to unfold. In the first moments of existence, temperature and density soared to infinity. Space and time themselves had no meaning. The four fundamental forces that govern everything today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, unimaginably powerful interaction, holding reality in a grip beyond comprehension. In a fraction of a second, smaller than the time it takes light to cross a proton, the universe underwent cosmic inflation, expanding faster than light itself. This was not an explosion into pre-existing emptiness. Space itself stretched, creating new dimensions as it grew, carrying matter and energy along like passengers on a cosmic conveyor belt. Temperatures were so extreme that the fundamental forces could not maintain separate identities. Gravity, electromagnetism, and the nuclear forces were all aspects of a superforce that has not existed since. As the universe expanded and cooled, this primordial unity shattered in a series of phase transitions, releasing titanic amounts of energy and establishing the blueprint of physics. Gravity broke away first, followed by the strong nuclear force, and then the separation of electromagnetism from the weak nuclear force. Within the first minute, temperatures fell enough for Big Bang nucleosynthesis, fusing protons and neutrons into the first atomic nuclei, primarily hydrogen and helium. Matter and antimatter annihilated each other in constant flashes of pure energy. While the universe remained opaque for 300,000 years, a glowing fog where photons could travel only tiny distances. Then came cosmic dawn. Electrons combined with nuclei to form neutral atoms, allowing light to travel freely for the first time. This clearing created the cosmic microwave background radiation, a faint echo of creation that still blankets the sky, whispering the secrets of the universe's birth. The Big Bang was not merely an explosion in space. It was an explosion of space itself, creating time, matter, and the laws that govern all existence. No event before or since rivals its power to conjure everything from nothing. Yet even this, cosmic genesis pales compared to the violence of hypernovae. When a star 50 times the mass of our sun exhausts its nuclear fuel, it doesn't simply collapse. Its death throes produce a hypernova, an explosion 10 to 100 times more energetic than a normal supernova. The energy unleashed is equivalent to billions of atomic bombs detonating every second for millions of years. These stellar titans are exceedingly rare, requiring both extreme mass and rapid rotation. As the core collapses, it forms a black hole almost instantly, but the star's spin prevents a symmetric implosion. Instead, an accretion disk forms, spinning at incredible speeds, generating magnetic fields of unimaginable intensity. Twisted like cosmic springs, these fields eventually snap and reconnect, launching jets of matter and energy at 99.9% the speed of light. These jets drill through the star's outer layers like cosmic drills, releasing enough energy to power our sun for billions of years. The jets escape into space, producing gamma-ray bursts detectable from billions of light-years away. Inside, the star. The shock waves ignite explosive nuclear fusion, burning carbon to neon, neon to silicon, and silicon to iron in mere seconds. This rapid chain of fusion reactions adds to the destructive power, producing an explosion visible at the edge of the observable universe. A single hypernova can forge more heavy elements than dozens of normal supernovae. The radioactive isotopes generated continue to decay for weeks and months, producing an afterglow that illuminates the surrounding cosmos. These stellar forges scatter essential elements for life across vast regions, while their shock waves can sterilize or trigger star formation across hundreds of millions of light-years. On scales far grander, galaxy clusters, the largest gravitationally bound structures in the universe, can collide at thousands of miles per second. Each cluster contains thousands of galaxies, trillions of stars, and superheated gas glowing in X-rays. The Coma cluster, for example, contains over 1,000 galaxies and a mass equivalent to 100 trillion suns. When such titans collide, the energy released surpasses the combined output of all stars in both clusters by millions of times. The collision unfolds over hundreds of millions of years. Dark matter, composing most of the mass, passes through almost unaffected, feeling only gravity. But the hot gas filling the intergalactic space crashes together at velocities up to 5,000 km/s. Shock waves heat the gas to over 100 million degrees, stripping electrons from atoms and creating plasma that shines brilliantly in X-ray light. Magnetic fields stretched and amplified during the collision accelerate electrons to near-light speed, causing them to emit radio waves as they spiral along the field lines, forming radio halos spanning millions of light-years. These events, hypernova, and galaxy cluster collisions, demonstrate the immense power at every scale of the cosmos, from atomic nuclei to galactic titans. They are the universe's ultimate laboratories, where the laws of physics are tested under conditions far beyond anything imaginable on Earth. The aftermath of galaxy cluster collisions is a ghostly spectacle, as vast clouds of superheated gas emit a radio glow larger than entire galaxies. The most violent encounters produce bow shocks, cosmic sonic booms racing outward at thousands of kilometers per second. These shock waves compress and heat the surrounding medium, sculpting structures visible across intergalactic distances. The energy unleashed in these collisions exceeds the combined output of billions of supernovae, a force capable of reshaping the very fabric of clusters. Within the clusters, individual galaxies are not spared. Tidal forces strip stars from galactic outskirts, forming long streams of stellar debris that trace the gravitational ballet of these cosmic giants. Some galaxies are completely disrupted, their stars scattered into the growing cluster halo. Yet even in destruction, there is creation. The collision compresses gas clouds, triggering massive bursts of star formation. These starbursts can accelerate stellar production by hundreds of times, painting galaxies with brilliant blue regions filled with massive stars that live fast and die young. Hidden beneath all this cosmic drama lies a threat more terrifying than any explosion: the Higgs field, the invisible entity granting mass to all particles. It might not rest in its lowest energy state. If it suddenly collapsed to its true minimum, it would trigger vacuum decay, an expanding bubble moving at light speed, rewriting the laws of physics, annihilating everything in its path. The Higgs field permeates every corner of the universe, even the vacuum between atoms. Like a ball balanced on a hill, it may occupy a false vacuum state, seemingly stable but poised to roll into a lower energy reality. If decay begins anywhere, the bubble of true vacuum would expand at the speed of light. No warning, no escape. Matter, energy, and even the fundamental constants of nature would be irreversibly altered. Particles could vanish, atomic nuclei would disintegrate, chemistry and biology would become impossible. The energy released could exceed the combined mass energy of all matter in the universe, flooding existence with power beyond imagination. Quantum mechanics ensures that if the false vacuum exists, decay is inevitable, a certainty over cosmic timescales. Some theories even propose that our universe is just one bubble among many, surrounded by realms governed by alien laws of physics. Vacuum decay represents the ultimate cosmic reset, erasing everything familiar in an instant. Yet, even amid such ultimate threats, the universe is home to ancient, violent relics from its birth. Primordial black holes. In the first moments after the Big Bang, tiny density fluctuations could have collapsed to form black holes smaller than atoms, but more massive than mountains. Unlike stellar black holes, primordial black holes can have almost any mass, from a paperclip to multiple suns. The tiniest of these objects are quantum-scale monsters, where the laws of quantum mechanics clash with general relativity. A mountain-mass primordial black hole, smaller than a proton, warps space and time millions of times stronger than anything we can create. Surrounding space-time twists into impossible geometries, regions where distance and duration lose meaning. As Stephen Hawking predicted, black holes emit radiation and slowly evaporate. Smaller black holes die faster, ending their lives in explosions of unimaginable intensity. A primordial black hole the size of an asteroid could release the energy of millions of hydrogen bombs, while one shrinking to subatomic scales would unleash more energy in a single second than the sun produces in an entire year, all concentrated in a space smaller than an atomic nucleus. If primordial black holes exist in abundance, they might solve cosmology's greatest mystery, the nature of dark matter. Invisible yet gravitationally potent, they could explain the unseen mass-shaping galaxies and clusters. Astronomers search for them in extreme cosmic environments. A black hole passing through a star would heat it, creating observable brightness. Changes. Collisions with neutron stars could trigger gravitational waves detectable from Earth. Over billions of years, some primordial black holes may have grown by accreting matter or merging with others. These invisible predators lurk in the voids between stars, bending and magnifying light through gravitational lensing, while the most massive ones may have served as seeds for the supermassive black holes anchoring galaxies across the cosmos, from galaxy-wide radio halos to the quantum fragility of the vacuum, from the tiniest primordial black holes to the largest supermassive anchors. The universe teems with forces both creative and destructive, reminding us that existence is a fragile miracle perched on the edge of incomprehensible power. Before the universe was even a single second old, space itself experienced an event so violent and extreme that it defies human comprehension. In a span shorter than the time it takes light to cross a proton, the cosmos expanded from a scale smaller than an atom to larger than a grapefruit. This period, known as cosmic inflation, unleashed the most powerful force ever witnessed, stretching the very fabric of space faster than the speed of light, and establishing the framework for everything that would follow. During inflation, Space expanded by at least 10^26 times in 10 or 35 seconds. To imagine it, picture a single atom suddenly growing larger than our entire solar system in an instant. The driving engine behind this expansion was the inflaton field, a quantum entity that filled all of space with enormous energy density. Unlike ordinary matter, the inflaton had the incredible property of producing energy as space expanded, fueling inflation with a cosmic supply that never ran dry. The larger the universe grew, the more energy became available to stretch it further, above, self-reinforcing force of unimaginable power. Inflation solved several long-standing cosmological puzzles. Before this violent expansion, the universe would have been riddled with exotic particles, magnetic monopoles, and topological defects, relics of primordial physics that we might still observe if not for inflation. But the extreme growth stretched these objects beyond the observable horizon, hiding them from our view forever. Inflation also explains the near-perfect uniformity of the cosmic microwave background across the sky. Regions that could never have exchanged energy after inflation appear almost identical, their uniformity a silent testament to the immense power of this early expansion. Quantum fluctuations in the inflaton field, initially microscopic, were stretched to cosmic scales, creating the tiny ripples in density that would later collapse into galaxies, clusters, and superclusters. In this way, the seeds of all structure in the universe, from the smallest stars to the largest galaxy clusters, were planted in the first fraction of a second after time itself began. The energy involved in inflation was truly staggering. In just this infinitesimal instant, the inflaton field released more energy than every star in the observable universe has produced over the past 13.8 billion years combined. When inflation finally ended, the inflaton decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10,028 degrees, a furnace so hot that particles were created and destroyed at unimaginable rates. Some theories suggest inflation may be eternal, with our universe just one bubble in an infinite multiverse, constantly giving birth to new regions of spacetime beyond our perception. Billions of years later, the universe gave rise to stars so massive and violent that even cosmic inflation seems tame in comparison. Deep within the heart of a dying star, spinning at 1,000 revolutions per second, magnetic fields a trillion times stronger than Earth's twist and coil, preparing to unleash destruction on a scale almost impossible to imagine. This is a magneto-rotational supernova, a rare and extreme event where rotation and magnetic power combine to create explosions far beyond ordinary gamma-ray bursts. As the stellar core collapses from Earth-sized down to just 12 meters, conservation of angular momentum spins it faster and faster, like a cosmic figure skater pulling in their arms. The magnetic field lines frozen into the plasma become twisted, amplified, and stretched to their breaking points, forming a cosmic dynamo capable of storing energy greater than the sun could release over billions of years. When these magnetic lines finally reconnect, they release cataclysmic energy, accelerating charged particles to near-light speeds and launching magnetized plasma jets across intergalactic distances. Unlike ordinary gamma-ray burst jets, these magnetically driven outflows maintain pinpoint focus, forming beams capable of sterilizing planets millions of light years away. At strengths exceeding 10^15 Gauss, these magnetic fields influence the very quantum vacuum of space, making it birefringent and splitting light into separate polarizations. Space itself becomes a cosmic crystal, with directional properties that do not exist anywhere else. Matter caught in these fields behaves in ways that defy reality. Atoms stretch into needle-like shapes, chemical bonds contort beyond recognition, and even fundamental particles act in ways no laboratory on Earth could replicate. The energy released by a magnetational supernova can exceed ordinary supernova by hundreds of times, forging exotic isotopes that last only seconds before decaying, creating elements essential to the chemical evolution of the cosmos. These events are cosmic alchemy at its most extreme, pushing nuclear physics to its absolute limits. Meanwhile, dark matter looms silently around every galaxy, outweighing visible stars by a factor of 5 to 1. Invisible to telescopes, it shapes cosmic structures through gravity alone, creating a hidden shadow universe that dictates the motion of galaxies and clusters. Should dark matter ever encounter its antimatter counterpart, the resulting annihilation could release energy so extreme that ordinary supernovae would appear as mere fireflies. From the birth of space-time itself, in cosmic inflation, to the most violent stellar deaths, the universe is a theater of unimaginable forces. Energy, matter, and the laws of physics are stretched to their limits, revealing a cosmos both beautiful and terrifying, a realm where creation and destruction dance together on scales beyond human comprehension. Dark matter, the invisible scaffolding of the cosmos, hides secrets that could rewrite our understanding of reality. If its particles are their own antiparticles, then when they collide, they annihilate entirely, converting all their mass into pure energy. According to Einstein's famous equation, even a single kilogram of dark matter undergoing annihilation would unleash energy equivalent to 21 million tons of explosives, a force so concentrated it makes nuclear bombs look like mere sparks. In the dense cores of galaxy clusters, where dark matter gathers like an invisible fortress, these annihilation events could unleash cascades of high-energy particles and gamma rays, saturating the surrounding space with radiation that outshines entire galaxies. Some models suggest that dark matter particles may be hundreds or thousands of times more massive than protons, compressing unimaginable amounts of energy into single points. When such particles annihilate, they generate showers of exotic particles and gamma rays that cannot be recreated in any Earth-bound experiment, potentially producing photons with energies so extreme that they approach the Planck scale, where quantum gravity begins to dominate. If dark matter annihilation preferentially occurs in regions of high density, the energy released could shape the evolution of galaxies, heating gas and preventing it from collapsing into new stars. Entire galactic centers could be sterilized, bathed in invisible yet incomprehensible radiation. Near supermassive black holes, where dark matter density peaks, these annihilation events might contribute significantly to the total energy output, producing high-energy neutrino and gamma-ray flares detectable across billions of light-years. In some extreme scenarios, cascading annihilations could empty vast regions of space of their dark matter content, leaving behind cosmic voids filled with pure energy, a silent monument to destruction. Far beyond this, in the visible universe, cosmic rays streak through space at velocities approaching 99.99999% the speed of light, carrying energies that dwarf anything achievable on Earth. Individual protons can carry energies equivalent to a baseball thrown at 60 mph, compressed into a particle smaller than a proton. The most extreme cosmic rays detected on Earth exceed 10^20 electron volts, over 10 million times the energy of the most powerful particle accelerator humans have ever built. A single particle contains enough energy to briefly light a small bulb, all concentrated in a subatomic nucleus traveling across the galaxy at near light speed. When these cosmic bullets collide with Earth's atmosphere, they create cascades of secondary particles lighting up detectors across thousands of square miles. But the origins of the most extreme cosmic rays remain a mystery. Shock waves from supernovae can accelerate particles to high energies, but they cannot explain the ultra-high energy cosmic rays. Instead, active galactic nuclei powered by supermassive black holes appear to be the only candidates capable of such acceleration. Their magnetic fields store energy on colossal scales, releasing it in bursts that propel particles along relativistic jets millions of light-years long. Natural particle accelerators far surpassing any technology we could imagine. Even after traveling for millions of light-years, cosmic rays are deflected by interstellar magnetic fields, making it nearly impossible to trace them to their sources. Only the most energetic particles, exceeding 10^19 electron volts, travel in nearly straight lines, serving as messengers from the universe's most extreme accelerators. Their interactions with magnetic fields produce synchrotron radiation, glowing across the electromagnetic spectrum. The radio waves we detect from the Milky Way, in fact, are largely produced by electrons spiraling through the galaxy's magnetic fields at relativistic speeds. Cosmic rays can be accelerated in multiple ways. Repeated crossings of shock fronts incrementally increase their energy. Magnetic reconnection, where twisted magnetic field lines snap and reconfigure, can accelerate particles impulsively. Some of the most energetic cosmic rays may arise from decay of exotic relic particles from the Big Bang, remnants of physics beyond the Standard Model, a hidden fingerprint of the universe's earliest moments. These particles collide with gas and dust, producing secondary particles, gamma rays, neutrinos, and positrons that carry information about both the cosmic rays themselves and the structure of the interstellar medium. Through these interactions, we glimpse the otherwise invisible architecture of our galaxy, its magnetic highways, and the turbulent seas of charged particles that sweep across the cosmos. And yet all of this drama unfolds against the backdrop of the quantum vacuum, a seething expanse between atoms, planets, and stars. Far from empty, this void thrums with invisible activity. Virtual particles blink in and out of existence, fleeting fluctuations that influence everything from particle masses to the evolution of cosmic structures. It is a realm where emptiness itself is alive, a stage for the universe's most subtle and profound forces. A reminder that even in apparent nothingness, reality is in constant motion, tensioned on the edge of chaos. Even in the vast emptiness of space, where no star shines and no galaxy glows, the quantum vacuum seethes with hidden energy. Virtual particles, ephemeral and ghostly, pop in and out of existence in moments so brief that they defy direct observation. Yet these fluctuations, operating at the smallest scales imaginable, contain more energy than entire galaxies and may ultimately dictate the fate of reality itself. The vacuum is never empty. It is alive with zero-point energy, vibrating even at absolute zero, a hidden reservoir of untapped cosmic power. Every cubic centimeter of space contains virtual photons, fleeting electron-positron pairs, and countless other particle combinations. They borrow energy from the vacuum, only to annihilate and return it before quantum mechanics can punish them for the transgression. This endless dance of creation and destruction generates an energy density that, if fully harnessed, would surpass the combined mass energy of all matter in the universe. The discrepancy between theory and observation, the cosmological constant problem, is staggering. Calculations suggest vacuum energy should be 10^120 times stronger than what we measure, an energy so vast that space itself would tear apart, and atoms could not exist. Yet the effects of quantum fluctuations are real and measurable. The Casimir effect demonstrates that two metal plates placed infinitesimally close experience a gentle push toward each other, a whisper of the quantum storm surrounding them. At black hole horizons, virtual particles can be ripped apart, with one swallowed by the singularity while the other escapes as Hawking radiation, revealing the incredible energy hidden in the vacuum. In the infant universe, these fluctuations were stretched by cosmic inflation, magnified from subatomic ripples into the seeds of galaxies, stars, and planets. Every particle of matter, every living organism, owes its existence to these ephemeral quantum tremors. Some theories suggest the entire universe itself originated from a quantum fluctuation, a brief deviation from nothingness that became permanent. In this vision, the Big Bang was not the beginning of all time, but a moment when a virtual universe became real, drawing energy from the vacuum and repaying it across billions of years of expansion. The quantum vacuum thus becomes not just a foundation for matter, but a cosmic forge of creation itself. The power of vacuum energy could, in theory, be harnessed. Advanced civilizations capable of manipulating space-time could extract this energy, generating effectively unlimited power. A device the size of a coffee cup might illuminate civilizations for billions of years, making every other energy source obsolete. The vacuum is a cosmic battery waiting to be tapped, a power source that exists everywhere, always and infinitely. Beyond our observable universe lies a realm so vast it dwarfs all known cosmic forces, the multiverse. If eternal inflation is real, our universe, home to galaxies, black holes, and gamma-ray bursts, is merely one bubble in an infinite ocean of realities. Quantum fluctuations in regions of false vacuum continuously ignite new universes, forming a cosmic tree of infinite domains, each with its own laws, constants, and destinies. In some universes, gravity may be stronger or weaker, stars and galaxies, forming in unimaginable ways. In others, the electromagnetic force may prevent atoms from existing. Some domains may allow elements and chemistry utterly alien to our reality. Within the multiverse, every conceivable physical law, every possible history, every potential outcome exists somewhere. The total energy of such an ensemble is literally infinite, a limitless expression of creation and cosmic power. Different universes may experience diverse fates. Some expand forever, drifting into cold oblivion. Others collapse back into big crunches, cyclically rebirthing themselves. Some oscillate endlessly, creating universes that pulse like cosmic hearts. Quantum mechanics hints at a further layer, the quantum multiverse, where all possible outcomes of every event occur simultaneously. Every split, every choice, every particle's path spawns a new branch of reality. Conscious beings observing. The universe inevitably find themselves in domains capable of supporting life, the anthropic principle in action. In a multiverse capable of communication, knowledge, and technology might transcend comprehension. Universes with different physics could harbor solutions to problems inconceivable in our own, offering access to infinite wisdom and unimaginable power. Yet even the multiverse is subject to cosmic processes beyond comprehension. Expanding bubbles of true vacuum might consume regions of false vacuum, a natural selection of realities in which only the most stable universes survive. This cosmic hierarchy, from the quantum vacuum to dark matter annihilation, from supernovae to hypernova, from black holes to the multiverse, reveals a universe that is violent, beautiful, and incomprehensibly powerful. Forces beyond imagination shape existence at every scale, from subatomic fluctuations to infinite realms of reality. And through it all, we are spectators, capable of witnessing only a fraction of the cosmic symphony, a fleeting awareness of the vast, relentless, and eternal power of creation itself. This convergence could ultimately lead to a state where all of reality aligns under a single set of physical laws, potentially ending the infinite diversity of the multiverse. From the subatomic dance of quarks to the violent collisions of galaxy clusters, we have traveled across scales so vast they defy comprehension, witnessing forces that shape existence itself. From the strong nuclear force that binds atoms, to gravity and dark energy orchestrating the motions of billions of galaxies, to the unfathomable potential of the quantum vacuum and multiverse, we have traced power expressed at every conceivable level. And yet the most astonishing truth emerges. The universe does not merely contain power. It is power. Every atom in your body exists because of forces so extreme they could annihilate worlds in a heartbeat. Every star that blazes across the darkness burns because nuclear reactions convert mass into unimaginable energy. Every galaxy spins. Every cosmic filament stretches across space because gravity and dark energy wage their eternal struggle across incomprehensible distances. And we, conscious beings, are not separate from these forces. We are their direct creation. The calcium in our bones was forged in stellar furnaces. The iron in our blood was scattered by dying stars. The gold in our jewelry was created in the catastrophic collisions of neutron stars, events so violent they shook the very fabric of spacetime. We are literally stardust, assembled by cosmic violence into beings capable of reflection, understanding, and wonder. Yet here we stand, aware of our origins, capable of contemplating forces that operate on scales both microscopic and cosmic. Perhaps the universe's most profound power is not destruction, but its ability to create complexity, beauty, and awareness. 13.8 billion years of cosmic evolution. Every supernova, every gamma-ray burst, every collision of black holes has converged to bring you, a conscious witness, into being. The question arises, what is the most powerful force in the universe? Perhaps it is not a single force at all, but the unbounded creativity of the cosmos. Its capacity to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into life forms capable of reflection and understanding. The universe does not merely exist. It learns, creates, and experiences through beings like us. When you look up at the night sky, remember, you are gazing at the ongoing struggle between forces that have shaped everything we know. And yet, you are not just an observer. You are a living testament to the cosmos's ultimate achievement. The universe's greatest power may lie not in its ability to annihilate, but in its capacity to know itself through conscious life. Even when we consider the titans of cosmic violence, the universe's scale humbles us. Gamma-ray bursts, the most energetic explosions observed, release more energy in seconds than 10 trillion hydrogen bombs detonated every second for the age of the universe. The brightest ever detected, nicknamed BOAT, brightest of all time, occurred in October 2022. Its energy saturated detectors across the solar system and even caused subtle effects in Earth's upper atmosphere from 2 billion light-years away. 2. Imagine this. Picture a flashlight from Alpha Centauri appearing as bright as a car headlight on Earth. That is the raw, almost unimaginable power of these cosmic events. And this light, traveling billions of years, carries news of stellar deaths from the early universe, when massive stars burned faster, died more violently, and seeded the cosmos with elements necessary for life. Some bursts trace back to a time, less than 1 billion years after the Big Bang, giving us a window into the universe's turbulent youth. Yet even these celestial titans pale in comparison to what lurks in the dark spaces between galaxies, hidden forces, invisible structures, and energy scales that dwarf even the mightiest gamma-ray bursts. The universe's power is limitless, layered and ever-present, a symphony of creation and destruction that stretches from the quantum foam to the infinite multiverse. And through it all, you are here, a conscious witness, part of the grandest spectacle imaginable. Every thought you have, every breath you take, every moment of understanding is a manifestation of cosmic forces billions of years in the making. In this light, the ultimate power of the universe may be revealed, its ability to know itself, to create beings who can marvel, comprehend, and celebrate its infinite grandeur.